So identify a subgroup of Z that we need to quotient it by to get Z4, and what are the cosets that are associated with that. So any subgroup of Z looks like KZ for some K in Z, K in the integers. So take a wild guess at what you guys think that K is going to be to get Z4. Justin, give me a guess.
I'm gonna say it's self.
Well, Z4 is it's a different entity, right? It's Z4.
Is that like Z mod 4, like modular arithmetic, or is that like 4?
Yeah. Z4 is Z mod 4.
Oh, okay.
So Z sub 4. I didn't feel like teching this up, and so.
Gosh, I feel a lot of pressure now.
Well, it has to be some integer K, and we're dealing with Z4. What K do you think it'll be?
4.
Yeah, exactly. So if we set K equal to 4, we get, what cosets does that generate for us? So it'll associate this will be kind of the most basic one, right?
Do you mean like when you say like 4, do you mean the subgroup like generated by 4?
Yeah, so this first off is a subgroup.
Yeah. I was just confused because like when you say like you needed the integer, you need to mod it out by, for some reason I wasn't like, I was thinking like you needed to mod it out by some subgroup, and for some reason I wasn't connecting the dots that you meant like the integer that generates a subgroup. You know what I mean?
Well, so what we're gonna find is essentially Z divided by the integer subgroup is just Z4. Oh, sorry, this is wrong. 4Z here.
Yeah.
So yeah.
But I just thought you meant like just like the element 4, and I was confused.
Okay. Yeah. No, the subgroup generated by multiplying the integers by 4.
Okay.
What are the other cosets that we get here?
Well, you're gonna get like 1 plus 4Z, like basically all the ones from like modular arithmetic force, like 1 plus, 2 plus, 3 plus.
Exactly.
Yeah.
So what, we have 1 plus 4Z. Two plus 4Z, and 3 plus 4Z. And 4 plus 4Z just brings us back around to where we started. So so this is negative 2, 2. Negative 1, 3. So that guy right there, or these are going to be the 4 of them. Okay, cool. So the same question here, but now we're mapping from Z10, so the integer is mod 10, to Z5. With the kind of the obvious one of the obvious function of n mod 5. So first off, what subgroup would you associate this with? First off, what subgroups are there of the Z10? Sophie, what subgroups are there of Z10? No? Lucy?
Not sure.
Come on.
So Z10, it would be the identity is one of them. You would have 5 in the identity. You would have 2, 4, 6, 8 in the identity. Am I missing one? I don't.
That's it.
So, yeah.
Oh, and then Z10 itself, technically.
Oh yeah.
4, 6, 8, and that's it. Cool. So which of these guys looks like it's going to be the most relevant for mod 5? That guy, the one that is just the group of 5, like it's the cyclic group that's associated with 5, right? So what cosets does this generate? So obviously 0, 5, and then if we add it up,
There would
1,
be
then we
5
get,
cosets.
yeah.
1, 6, etc.
Yeah, 2, 7, 3, 8, and 4, 9, right? And what are each of these guys going to get mapped to? What does this get mapped to?
0.
This guy,
1,
this guy,
2,
him,
3,
and
4.
cool. So these are going to be the 5 cosets that are associated with this, and the number of cosets is going to be associated with the order of the group that you're mapping to. So Zmod 5 has 5 cosets, so or it has 5 elements, so there's going to be 5 cosets associated with it. And yeah, cool. And now what about this? So Z cross Z to Z under this quotient group. First off, what does this quotient group look like? If you have the plane here, then you have 1, 1, you get 2, 2, you get blah, blah, blah. You also get 0, 0, you get -1, -1, blah, blah, blah.
Isn't that quotient group just isomorphic to Z?
It is isomorphic to Z.
Yeah.
So that does tell us something important. What would you just kind of naively, not even like in an abstract algebra sense, expect this to be isomorphic to?
Z.
Yeah, right? We basically have something that looks like z squared divided by z, and we would expect that to be equal to z. So just on a, even in a naive sense, you would expect whatever we get out on the other side to look basically like z. But what is going to be the quotient groups that come out, or what are the cosets that are going to be associated with this?
It's gonna be like 1 comma, or it's gonna be like all the um all the elements for which like the 2 points aren't equal. So like all the other lines.
Yeah, exactly. Or all of the other lines with slope 1.
Yeah, I'm not good at speaking.
You're fine. No, it's your intuition is exactly right. So we're going to get everything that looks like this, basically. So here, and we can basically define everything as a0 plus the group generated by 1, 1. So this is going to describe our cosets. And then we can just represent each of these by a. And another way to think of this is if we have the point x, y, then the map here is phi of xy is going to be equal to x minus y, right? Because it's for all of these elements, anything in this set, your x is going to be a greater than your y element, or negative a less, blah, blah. So what is the relationship between the kernel in all of these, the kernel and your subgroup? So what gets mapped to 0 in each of these?
The kernel.
Oh, that's what the definition of the kernel is.
Yeah.
But there's
It's what we're modding out by.
exactly. So we're modding out by a group. So in this case, we're basically modding out by z. In this case, we are modding out basically by 0 and 5. In this case, we're modding out basically by the multiples of 4. And in each of these cases, what we're modding out by is a group. So it's just all of the elements of those groups, of that group, get sent to 0. So for then phi of h is going to be equal to 0. The kernel is the elements of the group. The subgroup H. Does that make sense? Cool. So structure theorem for finite abelian groups. This guy, I believe you guys covered this on Monday, right?
Yeah. Oh, wait.
Sorry.
What day is today?
Wednesday.
Okay, yeah. Sorry. Yeah.
No worries. Yes. Gotta put that extra space there. So if I have a group of, someone give me a number, a pretty big number.
$900.
Okay, cool. 900. Group of order 900. What are the how many different ways can I decompose this? So let's first off give the prime factorization of 900. So that is equal to 2 squared times 3 squared times 5 squared, right? So how many ways are there for me to partition 2? Do you guys know what a partition is?
Can you go over that again? The partition part. Like, I get what they're doing, but I don't get like the relevance.
Well, so yeah, okay. So what a partition is, so let's say I have 3. How many different ways are there for me? Let's say I have 3 items. How many different ways are there for me to break up those 3 items? I can break it up so that there's 3 individual ones. I can break it up so that there's 2 of them and 1 of them. And then I can break it up so that there is just all 3 of them stay together. So there are 3 partitions of 3. Of 3. About 4. I can do 1. I can break them all up into 4 ones. I can break them up into 1 2 and 2 ones. I can break it up into 2 2s. I can break it up into 3 and a 1, or I can break it up into, or just not break it up at all, leave it as 4. So there are 5 partitions.
I don't get like how they were able to get from partitioning to like the actual theorem in the slides. Like that's what I don't understand.
So the theorem, are you talking about this theorem that I copied and pasted, or the one that tells you how many different partitions or how many different subgroups there are?
How many different subgroups there are? That one.
Okay, so how many different? So basically, if I have, let's say, I have, so I'm trying to decide what level of generality I want to show this in. Okay, so if I give you, let's go with 2 to the 4 times 3 to the 3rd. So what is that? 2 to the 4 is 16 times 27. So whatever this is. How this is, I want to know how many different abelian groups there are of this order. By this theorem, I know that it can be decomposed into finite groups that look like z to the p(e), right? So I'm going to ask myself how many different ways there are for me to break down 2 to the 4 into different multiples of 2. And I'm going to use basically the same idea as before. I can do 2 to the 1 cross 2 to the 1 cross 2 to the 1 cross 2 to the 1. I can do 2 to the 1 cross 2 to the 1 cross 2 to the 2. I can do 2 to the 2 cross 2 to the 2. I can do 2 to the 3 cross 2 to the 1, and I can do 2 to the 4, right? And similarly to before, I can do 3 to the 1 cross 3 to the 1 cross 3 to the 1, 3 to the 2 cross 3 to the 1. I can do 3 to the 3. So there's 3 different ways for me to partition this guy, and there's 5 ways for me to partition this guy. And then I can just mix and match them. And any way that I mix and match them is going to give me a distinct G. So that tells me the fact that I can mix and match these tells me that there are at least 15 by mixing and matching.
Wait, but I thought it said something about them being isomorphic to like the original group of that order or something, which I didn't find. I thought it said something about them being isomorphic, and then that's what didn't make sense to me, since they would have some of them would be cyclic and others wouldn't.
Oh, well, so it's just there are up to isomorphism. There are going to be this many, the partitions of each of. So if we have P1 to the, so let's say we have order G is equal to P1 to the K1 times P2 to the K2 times P3 to the K3, Pn to the Kn. To state this in kind of maximal generality, then we have the number of commutative of abelian groups up to isomorphism. So there are infinitely many groups that have that order. But up to isomorphism, there's only going to be there will be partition.
Wait, quickly, what does up to isomorphism mean again? I don't remember off the top of my head.
So basically, it just means, so Klein 4 is isomorphic to Z2 cross Z2, right?
Yes.
It means that I'm only counting these guys once,
Okay.
even though they are technically 2 different subgroups that have the same order. I'm only counting them once.
Okay.
Does that make sense?
Yeah.
So once you group together, basically there's this many, what, there's pi I equals 1 to n of the partitions of pi.
Oh wait, I thought yeah. I guess I was looking at them not as mixing and matching with the other partition of the other number, but just comparing them, and they're not isomorphic to each other at all.
Oh yeah, no, they're definitely not isomorphic to each other. Like
Yeah.
this guy is very different.
Yeah.
Not,
That's what was confusing me.
yeah. So those 2 things are very different, but that's actually kind of the point of it, that because these are non-isomorphic, when we generate the bigger groups using the cross products, they'll still not be isomorphic.
Okay.
So if I were to do this guy cross this guy and then this guy cross him, they would still be very different groups.
Yeah.
Does that make sense?
Yeah, that makes a lot more sense now.
Okay, cool. So what we were doing the 900 example. So this is actually an incredibly simple example because there are just 2 partitions of 2. Is equal to 2. We can have 1, 1, or we can have just 2. So how many different subgroups are there? How many different abelian subgroups up to isomorphism are there of 900? Well, it's going to be the number of partitions that I have associated with 2. The number of partitions I have associated with 3, and the number of partitions I have associated with 5. Yeah, exactly. So that's going to be 2 to the third is equal to 8. And we can actually just list off all of those. So we can have Z2 cross Z2 cross Z3 cross Z3 cross Z5 cross Z5. We can have Z2. I'm just going to change these guys to squared to save time on writing. Cross Z25. So Z2 squared cross Z9 cross Z5 squared, Z2 cross squared cross Z9 25. What we get Z4 cross Z3 squared cross Z5 squared, Z4 cross Z3 squared cross Z25, Z4 cross Z9 cross Z5 squared, and Z4 cross Z9 cross Z25. There you go. So that is all 8, all subgroups, or sorry, all abelian groups of order 900 are isomorphic to one of those. Yeah. So that is basically everything that I want to cover. Do people have any other questions? I will take that as a no.